Okay, so we're here for a short lab 2 part 4 video doing topographic differencing of these data sets. You're going to want to check that the data sets are all in similar vertical data sets and datums before doing this, and note any differences. I'm not going to ask you in this lab to realign the vertical datums if they're not in exactly the same orientation, but I would like you to look up how different those datums are on average, and think about that in your overall analysis and what you get out of here. And we'll talk about it in class as well. Okay, so how do we do topographic differencing? We've already done this profiling of the 3D elevation data, but what we'd like to do maybe even profile the difference map. Okay, so first we have to make a difference map. So what you do is you go to Tools, and you would go to Spatial Analyst Tools and Raster Calculator, which is under Map Algebra. It's the only tool there. I don't know why they just don't call it Raster Calculator. Okay, so what I ask you to do in the lab is use 2020 as the starting point that's closest to today and subtract the older data sets from it. So we can see if 2020 was greater than 2011, then the landscape went up in elevation. If it's negative, well, let's think about that again. So if 2020 is greater, it's going to be positive. So the landscape inflated. If 2020 is less, then it was higher in 2011. That means the landscape deflated or excavated out. And so that's, if we start with the most recent data set and go subtract from that, it's going to make the most intuitive sense for what's going on. So we would input a difference of the output USGS 1 meter clip minus the 2011 data. And we can call this diff 20 underscore 11, 20 minus 11, run. Putting it in the geodatabase, you can't start it with numbers, so keep that in mind. You'll get an error otherwise. So we're going to subtract those two data sets, and we'll see what's going on. Takes a minute. Okay, so there's my difference map. We did have some holes in the data sets, and so those holes can show through. Don't dwell on those. We see values in my case of 41.9 positive to negative 37.3. Most of the data is probably not that deep or tall, but we do have some areas, right, where there's huge excavations that have gone on, holes basically. Turn this off for a second. So you can see this is an excavation for gravel mining, and we also have piles, right, that have been put, and we can see those piles. If they're white, in this case, they've grown. If they're black, the holes are grown. So yeah, we're seeing difference right in there. To visualize this a little bit better, we could change the color scheme of this difference map. And so one way to go on that is like do kind of cold to warm. You could do some color gradients through there. And you could percent clip it, like can clip off, like try clipping off the 5% high and low to start maybe. So you can see maybe a little bit of more detail of what's going on. Like these fields are clearly taller, so they were active in 2020, and the vegetation was high. The LiDAR didn't see through it, so it looks high. Here, this must be a mound. Interesting. No, it's not a mound. So I guess the hole has filled in, or it was a deeper hole before. In this case, we go to purple. So that is a hole. So there should be a hole there. It does seem to have a hole. If we then zoom out a bit more, we can see my subsidence area up here. So if we broadly were to profile across that, we'd see the subsidence that's taking place across the landscape. So I'm going to try to do that now. So again, I can go back to map. I can add an elevation source. And this time I'm going to do my diff as my elevation source. And then I'll go back to analysis, and I'll go exploratory elevation profile, interactive placement, and I can then click that and draw across here. And we can see that 0, so no elevation change, is out here and roughly over here. And we can see this broad area where the landscape has gone down how much? 0.4 meters, so like 40 centimeters at the lowest over this region. But generally, kind of steps down to like 0.2 here. It's a little deeper as you go through there. So you can get a sense of the depth of the subsidence. So that's cool. We can go elsewhere. We could look quantitatively what's going on across these not subsidence areas, these gravel mining areas. Oh, I should say something else. It's often effective to turn off your background imagery. Just save your, it has to draw that every time. Okay, so let's profile then through, I'm gonna turn off this and look more at my visualization. So let's see what's happened in this gravel mine pit over those 8-point-something years. So mostly, we can see this area right here was excavated. The area over here really hasn't changed a lot. Maybe it's gone down a little bit. Over here, yeah, it was already a hole. Okay, here's a pile that was created, right? And so you can see what's changed. And so if we turn this back on, we can see there's that pile that we crossed, there's the hole, not much change. And so, yeah, interesting. Some other things, like look at this runway here. So there's the runway. Weirdly, it's taller there. So let me profile along the runway. So interesting, right? The runway, for whatever reason, was like jacked up in the middle and is taller. It's almost like a 20-centimeter cliff there. So I don't know exactly what happened, why it's like that. But it's definitely there. You wouldn't want it to be a cliff, so I'd be kind of curious to see how tight that really is. There's other weird things, like there's a little depression here. Maybe we could see some sort of erosion happening. I don't know. But, this LiDAR differencing could be showing us like maybe where there's some issues that need to take into consideration, right, with engineering or something. What else can we see in the landscape? We can see perhaps channel change along like, rivers going through the urban area. Like, what if I was to profile across this channel? Do we see anything? Okay, where's this? So we see some erosion here. That's along a road. Yeah. So along some sort of housing plat there up against the road, there's experienced some erosion. In the channel itself, there's some areas that might have experienced 10 centimeters of deposition. So we can see a little slug of deposit right there. So there's all sorts of things that you can look at in here. Now, the one thing I would caution you, right, differencing these LiDAR data is that one, we only use ground points. And so some areas that you see big areas, either just new houses appeared or houses were cut out. So keep that in mind. That sometimes the filtering of houses produce a lot of these splotches. And so it might not be what we wanted. Maybe we should have instead differenced the surface model, not the terrain model. We could look into the hills a bit. If we look in the hills, we might see kind of some interesting things. Like if I profile across here, we see some areas that look like they've got like deposits. Mostly it's no change. So I don't really know why there'd be deposits. Let's go where one of them is on the ridge itself, interestingly. And so I don't know. I suspect it could have something to do with vegetation that was or wasn't filtered out between one of the two data sets. Yeah. But I guess if we were going to do something in the hills, you'd maybe want to focus more in on areas that were smaller in scale. Like what about right here? So here you see 2020 is significantly higher than in 2011, right there on that edge for some reason. Maybe the data set's was too sparse to like see all that cliff or something. Because other parts of the data seem pretty much not much change. If anything, it's below, right? So that would suggest erosion, which makes more sense for the side of the hill. Okay, so yeah, that's a way to profile through your difference map. Another thing we can do with our difference map, instead of just, if we went back to symbology, we were doing percent clip to kind of hone in on these changes. Can also do classify is another approach, which gets you very specific quantifications. So we can get like a kind of similar map, but maybe more discrete if we add in like 10 classes or something, right? And then if we were to like kind of change it to manual interval, and we basically say what the upper values are going to be, we say, okay, anything above -20, it's here, and then -5 is here, and then -4, negative. Let's see some small scale stuff. Let's go to -2. Let's change this one to -1. And then we go to -0.5. We call this 0. And then 0.5. Okay, let's go back because this should probably be 0 to be more symmetrical. We'll just make this 1. 2, 5, and we'll go from there. I should have used one more class, but then this kind of sort of shows us where things are all the way I've got it, because that subsidence bowl is kind of tucked in with that 1 meter value. It's not sticking out, so it's not super helpful, right? We want to maybe look at that in more detail, and so maybe we want to like make this like 0. Negative 0.4, and then if we made this then negative 0.1, you can see this subsidence area sits here. We could hone in on that even more, but we can really see other things, right? So where different gravel mining is taking place and stuff like that, or something else might have stuck out in the landscape. And so classification is another way to go. Manual classification is probably the way to go. It's the most intuitive. Another approach would be the natural breaks, and then just add more classes. What if we did 20 classes? Then we might see some things, but you might then need to tune the colors to stick out more. And so you might do something like this, right? Where then random colors start to show up. That's the subsidence. Here we can see some homes. We can see like contours of the excavations in some cases. So there's lots of ways to visualize this change. If you want a quick and dirty, go to stretch and percent clip with a couple of colors. And what did we do? We did it in the end. I think we clipped 5% on both sides. That was pretty good. It allowed us to see quite a bit. Okay. Yeah, so you're going to difference all of the data sets from 2020. I'm curious to see if you see any more or less subsidence over that time. You could probably see what areas have had change over different time periods in terms of gravel mining, things like that, potentially channels or other development in the urban area as well. How do you potentially quantify this more? Well, these are vertical heights, right? You know, the pixel sizes are all 1 meter, 2 potentially. In this case, they definitely are, because both inputs are 1 meter. If you multiplied whatever that vertical height change was times 1 times 1, you actually get volume of change. You could see whether the landscape as a whole went up or down by doing that, and then looking at the statistics. You could also clip this to the area of the subsidence, and you could try to measure the volume of storage lost in the aquifer here. You don't have to do that, but I'm just trying to outline areas that you could, ways that you could make things more quantified. You could do the same thing, figure out how much area was excavated for one of these little gravel mining pits by like zooming in and subsetting your data set. You could also even potentially look at the height of some of the crops at the time the LiDAR was flown. So anyways, lots of things to explore in here. And so have fun doing that. I'm going to stop this tutorial for now. I'll make some more tutorials about linking maps later, but I'm not going to do that today.